So today we will move towards understanding the quantization of other fields. For example, we have discussed quantization of scalar fields, but in today's lectures onwards, we will try to go to different kinds of fields. For example, Dirac fields, which talks about fermions, and later on in coming week we will be discussing about the gauge field quantization, which is the electromagnetic waves or electromagnetic light quantization. Before we proceed to the quantization of different fields, we would like to just get some hands-on with the exercises on quantum fields. And in order to do that, we will just set the platform with exercises on scalar field itself. Since we have done the scalar field quantization afresh, so things are much more clear in our head to go with ahead with the computations. And in order to facilitate the computations with ease, I will just point out certain things which I should have done in the previous classes, but we missed out. But anyway, it is a good point here to clarify those ideas and move forward. So remember, how did we achieve the quantization of the scalar field? First, what we did, we anticipated that the operator phi, which gives me operators at each point of a space-time and at all time. So there is an operator, field operator, which gives you a scalar operator at all points of space-time. That we anticipated as a time-dependent operator in the Fourier space. So we have written phi k of t and then did the simple Fourier transform to land up on the position space-dependent operator. So this is how we anticipated how the operators will be talking, meaning how the operators in real space and Fourier space are related via a Fourier transform. Now what it happens that this operator in the position space was supposed to satisfy the Klein-Gordon equation, and in order to do that, the Fourier counterpart of that, which is phi k of t, would be satisfying this differential equation, which is the equation of motion of a harmonic oscillator, if you recall. So that is how we understood that the real-time operator, a free field operator in position space, is a collection of harmonic oscillator in Fourier space put together. This Fourier transformation is just a limit of sum. So these are infinitely many oscillators together constituting the position space operator. So far so good. That's how we had proceeded forward to learn about the quantization of the field. Then we quantize this harmonic oscillator like equation just like we quantize harmonic oscillators. That means we wrote down phi k as set of AK and AK dagger in order to make these phi k's just like oscillators. However, at this stage we should have been careful, which I had not alerted you people in the that point, but let me alert at this stage that when I am doing this and making an analogy with position space oscillator x double dot omega square x is equal to 0, on equation level they are looking exactly the same thing. However, remember when we wrote down x as root under h upon 2 omega times ak e to the power minus I omega t, not k, there was no k for position space. So a e to the power I omega t, a dagger e to the power I omega t. This way when we write, this is an inherent writing for a operator x which not only satisfies the differential equation for a harmonic oscillator but is also a Hermitian operator. So x is supposed to be x dagger. That's why this a and a dagger with complex conjugation factors coming together with them has appeared. This kind of decomposition ensures that the related operator x is a Hermitian operator. Do we need to demand that for the field operator in Fourier space? That is not very clear that we should be applying to that for field operator in the Fourier space. I know that the field operators in position space should rather be Hermitian operators. So what I want is phi in position space should be equal to its dagger in position space. That does not mean that its Fourier counterpart will also be Hermitian. So phi k dagger, this is not implied. If this is demanded, this will not be true. Actually, if you can see that if you demand that phi is equal to its dagger in position space, its Fourier counterpart satisfy a certain relation that phi kt is phi dagger of minus kt. So it is not just plain simple conjugation it undergoes. K goes to minus k under dagger operation. So the phi k operator is not Hermitian if we demand phi x operator to be Hermitian. And that is the cost we have to pay and we have to live with. That's why now on I would not write ak plus ak dagger, because that was ensuring hermeticity of the operator. Since I do not want hermeticity in Fourier space, I want this relation in Fourier space. So I should find out what should satisfy, what should be bk, whether it should be ak dagger or something else, in order to make the position space operators Hermitian. Okay, so that is what we are going to do, that I'm going to enforce this demand that phi k dagger is equal to phi of minus k. That you can work out easily, will ensure that b of minus k over here is equal to ak dagger. That means bk is a minus k dagger. Okay, so this is the choice we can move forward with. So we have the statement that for real space, real scalar field, there could be different kinds of scalar field, complex scalar field, real scalar fields, which have different properties. For real scalar fields, this property is essential. That means phi k will become this. This phi k, which was sitting over here, is going to become this object where ak will be coming with e to the power minus I omega t, and a of minus k dagger will be coming with e to the power plus I omega kt. Okay, and then the business as usual, whatever we have done for operators, moment, conjugate momenta and other things, that should follow from there onwards. So the cost of working with real scalar field over here is this. I will write down the pi like before, which would be the derivative operator on phi, and it will again be giving me some minus I omega upon c kind of things, which this time only you have to be careful that ak dagger has been replaced by a of minus k dagger. Previously, what we were writing for was a Fourier space Hermitian phi k. That is not a real phi x, which would be some complex scalar field, but that is not what we want. So I'm specializing for real scalar field in position space. So the cost would be wherever ak dagger was appearing in the previous thing, a of minus k dagger will start appearing over there. So this therefore will become my decomposition structure for real scalar field. So whatever we did in the previous classes, you have to just correct your notes, rather not correct your note, but specialize your notes for a real scalar field. The decompositions becomes something like that. All right. And one more thing, what you can play a trick upon, let us look at this term and this term. The first term is ak e to the power minus I omega kt e to the power I k dot x, and there is a outside integration d3k and root 2 omega k. The second term is similarly d3k root 2 omega k, a minus k dagger e to the power minus I omega kt plus I omega kt rather, and e to the power I k dot x. Now what you can do in this thing, in the second piece, what you can do is do a variable transformation k going to minus k. Under k going to minus k, you know d3k goes to d3, it doesn't change at all, meaning all the limits go from minus infinity to infinity, kx, ky, kz still, and root 2 omega k depends on the vector k through its magnitude, so it would not change at all. So therefore only thing it will happen under this k going to minus k, the vector k going to minus vector k, this integration can be written as ak dagger now. Previously it was a minus k of dagger, then I plus I omega t minus I k dot x. So I have just flipped the sign of k everywhere, and therefore this will therefore become, the full thing will become ak e to the power minus I omega kt I k dot x plus ak dagger and the complex conjugate of this function which is appearing over here. Similarly for momentum operator as well. So here when I put a common e to the power I k dot x, then I would work with a minus k dagger. A minus k dagger in both sides. Alternatively, I can just bring these things in here and here and do a variable flip in the second integral, so that I will have a ak times something plus ak dagger times complex conjugate of that, and so on. So do not get surprised if you see such things appearing in my notes as well, that I would write phi, real scalar field phi, as either this decomposition in the box I have written over here, or ak e to the power minus I omega t plus ik dot x plus ak dagger e to the power plus I omega t minus ik dot x. Both are same thing for real scalar field. So let us move forward with this understanding. I will just summarize in terms of how to write Hamiltonian for real scalar fields and other things, and then we will move on to do some exercises. So as we saw, for this setting, I would get the harmonic oscillator Hamiltonian, which will be h omega k, h bar omega k, and the number operator for each k mode, and then there is a vacuum energy for each k mode that would be coming about. And the box here tells us the usual way of variables again, but we have discussed previously. So here you see I have done this decomposition which I was talking about. Ak times e to the power minus I omega kt plus ik dot x, and just Hermitian conjugate of that term over here, such that the phi in the position space becomes Hermitian. And similarly, you can see that this and those things are complex conjugate of each other. This time they are coming with a minus sign. To compensate for that, I have iota over here, so that the pi here as well is a Hermitian operator. So now, with this choice of variables and the selection of the operators relation with each other, I have a real scalar field. Previously, we were discussing about a real Fourier space field, which would have been a complex scalar field of a special kind. That would not be most general complex scalar field. But in this course, we are not going to discuss about complex scalar field. Those become more interesting for gauge field theories interacting with particles, if a scalar field has a charge or something. However, we are not going to deal about that more in more details. We will touch upon on that. So therefore, most of the discussions I'm going to base upon in this course is for real scalar field. So this box, therefore, is a good set of information for real scalar field. You can come back again and again to just cross check your structure, that I have a Lagrangian for a real scalar field, which is given by this. The field operator is written in terms of creation and annihilation operator like this. Its conjugate momentum is this. In Fourier space, there is a harmonic oscillator structure for each different k, and their frequency are related to the mass and the k, right, like this. They satisfy the standard creation annihilation commutation relation, and with these choices, we land up on a collection of harmonic oscillator Hamiltonian, which is all like that. And with these choices, the Lagrangian is obtained through the integration of the Lagrangian density first over the volume and then over the time. So this is the whole package for a real scalar field. Similarly, one can construct a package for complex scalar field as well, complex scalar field of the kind which we discussed as well. So you can do this as at your leisure as an exercises, but for now we are going to go ahead with the exercises of computations for real scalar field. Okay, so now what we have learned previously as well, that for now each oscillator, for example, oscillator with identified with wave number k, it can have a vacuum state 0 of k, or it can have a first one particle excited state, or two particle excited state, or three particle excited state, so on. And similarly for k primed as well, there can be vacuum at k primed, or one particle can be excited at k primed, or two particles could have been excited at k primed, and so on. So these are the structure for different k. A full state of the field has to tell me exactly about in which k modes how many particles are there. For example, a typical psi could be, let us say, 0 particle in wave number k0, 1 particle in wave number k1, then 0 particle in wave number k2, and then similarly 3 particles in wave number kn, and so on. So these are infinitely many different harmonic oscillators with identified with number k0, k1, k2, k3, k4, kn, infinitely many of them. You can think of it as a collection of 3 harmonic oscillators would have a state first particles, first oscillator state, second oscillator states, and third oscillator state. Similarly, we are doing for infinitely many of them. This could be one possible structure, or I can put some coefficient over here, C1 plus C2 could be some 3 particles in K0, 1 particle in K1 again, and 2 particle in K2, no particle in Kn. So all different combinations you could try are possible or are plausible set of wave functions which a field can have. This is a decomposition for oscillators in Fourier space, but there is a one-to-one map to the position space as well. If I want to know what does the field operator does on these states, I would have to act phi operator on this. So that is what we are going to do. And a good choice of a state to learn many things about is a vacuum state. Vacuum state is all the oscillators are there in their ground state. K0 is also having no particle, K1 is also not having any particle, K2 is also not having any particles, and so on. So this is a unique state. Vacuum is a unique state of the theory, and most of the things which we want to know about the structure, which we will be interested about in this course as well, will revolve around vacuum. So in this course, we want to know what the quantum field's intrinsic structure does onto the system. When we apply electric field, more or less, we know what the atom does. The Stark effect or Zeeman effect, where we apply electric field or magnetic field. The structure which will be most interesting for us is when we do not apply anything. Then also there should be quantum fluctuations in that. And those quantum fluctuations will be coming from a state of a vacuum kind, where nothing is excited, everything is in vacuum. So this is a good choice of a state to work things with, and we are going to do most of the business with this. And we will see, even if you take states like psi, like this non-vacuum state, many of the properties of the non-vacuum state stem from their structure in the vacuum state itself as well. This will become clear as we go forward in the course, but as of now I'm going to do business starting with a vacuum state. For instance, I would want to know what is the field doing, what is the structure of the field operator in the vacuum state. So one way to answer that is that obtain the expectation value of the field in the vacuum state. So what I would do, I would first decompose phi in its harmonic oscillator avatar and then squeeze it between the vacuum state. So therefore I have written phi as a collection of infinitely many harmonic oscillators, something which we have learned to do, and then squish that operator between the vacuum state. Remember, this vacuum over here means this. So let me just first make a clean identification mark on this, that vacuum means, so vacuum means this state. So each of the operator AK will search for its own counterpart state. That means AK1 will try to find what is the state structure in the K1 thing. So it will find no particle here. Similarly, AKN will try to find what is happening over here, and it will find no particle in Kn as well. So all of the Ks are put to vacuum, and different AKs running with the changing of K will search for the corresponding structure of state in their individual Hilbert subspace, let us say, or Fock basis element. So therefore, the structure is like this. This vacuum state is just a this acronym of this expanded version, and ultimately what will happen is that I will have this operator squeezed between 0 and 0 from left and right, and this operator squeezed between 0 and 0 from left and right. Okay, and e to the power I omega t I k dot x. In field theory, position is not an operator, time is not an operator, k is not an operator, and omega is not an operator. So they will go out. This integral will also go out. So I will have two terms, one with 0, ak 0, and then e to the power minus I omega t plus kx. And the other is 0, ak dagger 0, and e to the power plus I omega kt minus ik dot x. Out of these two terms, the first term will vanish because AK annihilates the vacuum. So remember, this AK is being integrated over D3K. That means it is AK1 plus AK2 plus AK3 plus AK4. Under this integration, it means different AKs are coming and hitting this 0, and they are trying to find out in their corresponding wave number what is the configuration of the state. It will find for wave number Kn, let us say it will find there is a vacuum, it will annihilate that. So for all operators coming under this integration, each time this annihilation operator will find the vacuum acting upon and kill the state. So therefore this first squeezing will not survive. Only the second squeezing is going to survive, and which is this. Okay, AK dagger squeezed between 0 and 0. But you see, AK dagger hitting the 0 from the left is just the Fourier counterpart, or not Fourier complex, Hermitian counterpart of this statement. If you write this, this will become 0 AK dagger. Okay, but we already know this thing is 0 and its dagger should be 0 as well. Therefore this operator is also annihilating the bra 0. The AK dagger annihilates the bra 0. AK annihilates the ket 0. AK dagger will annihilate the bra 0. So therefore even this squeezing will not survive. That means in the vacuum state, the field does not have any expectation value. It has a 0 expectation value. So there is no expectation value in the vacuum state. Okay, this looks like a good definition of a vacuum, that there is no expectation value which is surviving. But see, this is not a very unique statement about vacuum. For example, if I do one particle excited state which is non-vacuum, that means one of the K, let us say K first, K naught, I try to excite now. So let us say this state I'm going to talk about, which is psi 1 K naught. This state will be called collectively 1 K naught because all other things are in vacuum. If I compute 1 K naught expectation value of the field in the 1 K naught state, so just let me correct the, just rewrite what was vacuum such that this detour was just to tell you what is 1 K naught state. So once we have identified what is 1 K naught state, I will squeeze operator phi k between these two things. So previously you saw that AK and AK dagger operators were getting squeezed between vacuum from both sides. This time they will get squeezed between AK 1K naught, 1K naught from left and right. And what more, 1K naught, the state 1K naught can be written as AK dagger at wavelength K naught acting on vacuum. So vacuum used by creation operator excites one particle into wave number K naught. So I'm going to write the state 1 K naught as AK naught dagger, and similarly its bra, which would be Hermitian counterpart of that, would be vacuum AK naught coming from the right. This is not 0. Had it been an AK dagger, then it would have been 0, but if it is AK, this is not 0. Similarly here, this is non-zero. AK dagger hitting the ket 0 is not 0. Had it been only AK, if this was not there, then it would have been a 0 as well. But right now they survive. Okay. So fine. So let us go ahead and see, once they survive, what do they tell us about its structure. So you see now I have three operators, one AK coming from here, then AK coming from here, and then AK dagger coming from here. They get squeezed, and similarly for this term, AK not coming from here, AK dagger coming from here, and AK dagger coming from here, that gets squeezed between vacuum. So now we have a three objects squeezed for the first term and three objects squeezed for the second term. First term is AK, AK naught, AK naught dagger, AK naught, AK naught dagger. And this exponential factor and the integration are tagging along with this. And the second term is AK naught, AK dagger, AK naught dagger. So AK naught, AK dagger, AK naught dagger, and this exponential getting tagged along with this. Okay. Now the crucial and important thing is this. Previously I had a single AK which was getting squeezed between vacuum and single AK dagger which was getting squeezed between the vacuum. This time we have three of them getting squeezed between the vacuum. Now what you can do, you can try to find out what happens to these terms. I have a AK and AK dagger here. AK and AK dagger here can be flipped using a commutator, because we know AK and AK dagger, let us say AK not dagger, commutator would be delta of K minus K naught. That means AK dagger, AK naught dagger rather, would be equal to delta of K minus K naught plus AK dagger, AK naught dagger AK, which is this. Okay, the same thing over here using the commutator can be written like this. What do we earn out of it? First of all, AK has come on the right hand side. That will annihilate the vacuum, because I know whenever AK hits the vacuum, it kills it. Previously, AK not dagger was coming on the right hand side. It was not annihilating the vacuum. Using the commutator, I flipped things, and therefore it annihilates that. So I'm not worried about this term anymore. What about delta KK naught? Delta KK naught is not an operator. It is identity. So this will also not do anything. So I will have just AK naught surviving with a delta KK naught, delta K minus K naught, which will come out, and 0 AK naught 0 will be there. Again, AK naught is hitting the 0. So it will annihilate that. So therefore the whole term over here, the three operators squeezing is 0. Similarly, you can verify even for the second three operator squeezing over here, that is also identically 0. So that means even in the first excited state, the field expectation is 0. Okay, you can see the vacuum, the field expectation was 0, which was good for us, but there are other states as well where field expectations are 0. This is not surprising, because in harmonic oscillators also you know that in vacuum state, which was something like a Gaussian like this, the field expectation is 0. But for any symmetric wave function as well, if you can think of a symmetric wave function, there also if you find out, the field expectation remains 0. The harmonic oscillator expectation remains 0. So harmonic oscillator ground state, X operator in the ground state of harmonic oscillator is 0. But it is not unique to ground state only. There could be other excited state. Remember, X expectation in position space means dx x psi of x mod square from minus infinity to infinity. If this psi of x is a symmetric function, then overall function becomes odd, and odd function under integration from a minus infinity to plus infinity is 0. So any symmetric function will also make the expectation value of the field of the oscillator 0. That is what exactly happening here. This 1k naught is not vacuum, but its structure is something like that of a symmetric state in the oscillator structure. So therefore, field expectation being 0 is necessary for vacuum, but is not sufficient for vacuum. You cannot claim that if field operator's expectation is vacuum, that means we are talking about vacuum state. Oh, sorry. If the expectation value of the field operator is 0, then it necessarily does not mean we are talking about vacuum state. There can be other states as well whose expectation value remain 0 in those states. Okay, so the field operator's expectation value is not going to distinguish between vacuum and a similarly poised or similarly expectation profile non-vacuum state like 1k naught and even 2k naught, 3k naught. If you can try to find out for all those states, you would find out that the field expectation is vanishing. So there are infinitely many states where field expectation vanishes. In fact, if you do the exercise for the conjugate momenta operator pi as well, for example, this pi operator, whose decomposition which we have learned previously how to write again in terms of AK and AK dagger, which is over here. Then also the same story will unfold. If I take pi and it squeezed between 0, then either single AK will get squeezed between 0 or AK dagger will get squeezed between 0, and they will annihilate the vacuum state like the phi operator does. So even the pi operator would be having a 0 expectation value in vacuum. Okay, and this is again the same computation. You will see only the exponential factors. There is a relative sign between AK and AK dagger for pi. nothing more. There is a iota and there is a complex conjugate minus, but individually both these operators which were being added for phi and getting subtracted for pi, these are the operators which are getting added for. So this operator and this operator get added for phi, and the same operators get subtracted for pi. So the operators are the same. The operators which are constituting phi and pi are the same, just there is a relative sign difference. However, what we saw that the operators themselves get squeezed between the states 0 or 1k naught to get annihilated. So that becomes 0. So the same thing will be true for pi as well. And therefore, you will realize that the pi also has a 0 expectation value either in the ground state or in the 1k naught state or 2k naught state, 3k naught state, what we talked about. So field expectation value or its conjugate is not going to differentiate between the vacuum and its excited state of the similar profile. So we need more operators to distinguish between a vacuum and non-vacuum states. Phi and pi are not able to distinguish between vacuum and a non-vacuum state. So one such operator could be the Hamiltonian. The Hamiltonian operator between the vacuum, squeeze between the vacuum state or the non-vacuum state of the kind which we have discussed, 1k naught. Both these squeezings are non-zero. Why is that? You can see that the Hamiltonian operator itself is made up of two pieces. One is the number operator, ak dagger ak, this is the operator, and then there is identity operator times delta 30. Okay, so this object over here is some surviving operator, meaning it will not be going to 0 for any state because it is identity. So this delta 30 times half is going to survive always, unless this ak dagger ak expectation cancels it. But I know this is a number operator, and number operator is bounded from below to be 0 or above, meaning it cannot be taking negative value. So there is no case where Hamiltonian can become 0. So Hamiltonian will come at least with this much of energy value, and that is the case for the vacuum state. If I take the Hamiltonian, squeeze it between the vacuum state, I would have two operators which will be surviving. One is ak dagger ak, which is the number operator squeezed, and then there is a half times delta 0 times identity operator which is squeezed. This will be going to 0 because of this again ak annihilating the vacuum state. However, the second part will be surviving, and that will ascribe some energy to the vacuum state. So therefore, the energy of a vacuum state is given by the expectation value of this will be obtained as half times d3k h bar omega k and delta 0. This delta 0 is the delta function in the Fourier space. So that is proportional to the volume of the position space. So you see that this is the Hamiltonian energy density and total volume multiplied together give you the total Hamiltonian. And this is the energy the total Hamiltonian comes up with, or this is the energy density vacuum state comes up with. Okay. However, once we do for the 1k naught state, previously the two operators were getting squeezed between 0. This time they will get squeezed between 1k naught. So I will have a term which is 1k naught ak dagger ak 1k naught, and there, so remember there is an integration d3k upon times h bar omega k, and then there is a half term which is also there. So sorry, this is 1k naught and delta 0 times identity on 1k naught. So this is still going to be half times delta 0, while this time this operator ak dagger ak, which was getting squeezed between 0 previously to become 0, this time it will not be 0, and it will exactly give you, if you do this exercise slightly carefully and pay attention to what we are doing, you will get a delta 0 times 1. So overall it will become 3 half d3k h bar omega k delta 0. So the Hamiltonian operator separates the two states. The field operator doesn't. The conjugate momenta operator doesn't. They give you the same expectation value, which is 0, but the Hamiltonian tells them apart. That the vacuum comes with the minimum energy possible, which is this. There is a one particle excitation, which gives you additional energy cost per unit volume of 1, or 1 meaning h bar omega k for each k, and in the whole space the delta 0 volume multiplied. So overall it becomes 3/2. So therefore we can have different operators which will try to describe different expectation value, and also presumably the fluctuations or variances in them. So we can try to find out what is the variance in the vacuum state, what is the fluctuation, what is the correlator. One interesting object which we will need and we will see later on is 2-point correlation, that phi x and phi y in the vacuum state or any other state. Most of the time we will discussing about vacuum as we discussed, but this can be computed in any other state. This is an analog of x of t and x of t primed in harmonic oscillator. So these kind of 2-point correlator is like two different position correlators in harmonic oscillator, which will be interesting and handy. Those kind of things which will be important, we will learn in coming weeks. But as of now, this is the standard way we can compute things using the property of annihilation operator and accretion operators and their commutation relations. In the next class, we will just wrap up the discussions on the calculational aspects, trivial calculations aspect, by discussing conserved charges, conserved quantities in these kind of actions, the trivial field theory action.